Thank you, Jacqueline, for a very, very kind introduction. And hello to everybody in Australia from a very cold and about to be snowy Dublin, Ireland in the middle of the night. I'd like to talk to you about the energy transition, implications for geoscience, a view from the north. So, echoing Jacqueline, I'd also like to say that yes, today is the United Nations International Day of Women and Girls in Science, and that throughout the geoscience industry and in society, we need to eliminate barriers for females throughout the world. So, what I want to talk to you today about the energy transition, three main themes. What is it and why? Its impact on research and the effects from geoscientists. And this will be a view from the Northern Hemisphere, but I hope there's some things I can say that will also be of interest in Australia as well. So first, the introduction went through many of the things, but I just wanted to say, who am I to speak on the energy transition? I do have a varied background. On the far left, you can see the oil well. I literally grew up in an oil field in northeastern Oklahoma. My grandfather was a petroleum geologist. My father was a research microbiologist for a mid-tier oil company. So I sort of have it in my blood, I guess, a bit. Nonetheless, when I went to college, I wanted to be an anthropologist, not a geologist. But I found that I couldn't do my research in Central America. There was no way to fund it. However, the school I was at, their field camp was in Central America. So I became a geologist, so I could go to Central America and do the research I wanted to do in anthropology. It turned out that I actually love geology too. I ended up doing an honors thesis mapping active volcanoes in Guatemala, and that was pretty neat. So then went to do my master's and my PhD, ended up working sort of a different part of the world, the Brooks Range, northern Alaska, north of the Arctic Circle, on volcanogenic massive sulfides, so ancient volcanic rocks, and then my PhD on a carbonate-hosted copper cobalt deposit. When I did that work with Anaconda, and in sort of what was a number of transitions that we all have in our life, the year I graduated with my PhD, Anaconda, who had supported me, went out of business. So I ended up working for Chevron Corporation, and I worked around the world. The middle image there, you can see me in the early 80s in Papua New Guinea, and I'm sure a number of you in the audience have actually worked there as well. I was lucky enough to work all over the world with Chevron, doing primarily minerals, but I also worked on geothermal in California and Indonesia, and I became a carbonate reservoir specialist for the company too in the petroleum side. My last real big job with Chevron was in Ireland, where I did discover the Lisheen deposit, took it through pre-feasibility and got it ready for mining, and you can see a picture there of the mine as it finally developed. After that, I was a bit burnt out, so I decided to do a fellowship, first in the Senate, then in the White House. Clinton won, working in the Office of Science and Technology Policy. I was a natural resources expert for them and also worked on climate change issues with Vice President Gore's group. After that, I decided not to return to Chevron, but to go into academia, something I never thought I would do, and went to Colorado School of Mines, where I taught economic geology, energy policy later, and worked in a whole bunch of different research projects around the world with a huge cadre of great students and other great professors in a number of departments: geophysics, mining engineering, petroleum engineering. After a number of years, my wife, Maeve Boland, also had become interested in geoscience policy and had moved to Washington to do a fellowship and then become a policy analyst and policy specialist. And after a number of years commuting from Colorado to Washington, I thought it was time we actually were back together. So I accepted a job, took a job at the U.S. Geological Survey as the Associate Director for Energy and Minerals. That was in the last year of the Obama administration. We then had an election, and as everybody knows, certainly at the present time, we got an interesting president. I lasted with that president not a full year. At the end of 2017, one of the political people asked me to do something I felt was unethical, so I resigned. I was then very lucky that people in Ireland remembered me, and I was able to get the position at University College Dublin and become director of the iCRAG, which I'll talk to you about later in the talk. So the energy transition, this is actually how it's viewed by many. From the left there, we can see grays and dark colors and the evil fossil fuels, right? Transitioning to the bright sunshine of windmills and waves and solar panels. That's a little bit simplistic, I'm afraid. So why are we in the energy transition? Well, there is a climate emergency. It's been declared by several countries. You can see on this map, most of Europe, Canada and Argentina. And then in the pale blue, and a number of island countries as well have declared. And then in the pale blue, Australia, the United States, Brazil, are areas where parts of the countries have actually declared a climate emergency. So what is the energy transition and why is it happening? And this slide really sort of sums it up. It's because of population. We've got a lot of people on the planet. And so back in January of 2002, Paul Crutzen in Nature wrote an article trying to define the Anthropocene. And he defined it basically as the late 18th century when analysis of air trapped in polar ice showed the beginnings of global concentrations of CO2 and methane. And that's a good scientific way to do it. Another way, if you look at this curve, might be to say the Anthropocene started when human population exceeded 1 billion people. It's about the same time. But you can see the asymptotic rise there since basically the 17th century. And with that rise in population, obviously came other things that rose. So energy use and CO2. So both those actually went asymptotic at about 1950. So they're delayed from the population. After World War II, when there was really great economic boom around the world in the 50s into the 60s and to today. So the energy transition, there's all sorts of different ways people have looked at it and what's happening. One thing to say is it is a transition. It's going to take time. So in this particular individual's view of where we're going or where we've been, notice that they put the coal peaked in 2014. So that's basically total coal usage in the world. They're predicting the oil will peak in 2 years, in 2023. That natural gas will peak in 2034, and we'll go from where we are now, where we have approximately 20% of the energy mix in the world is non-fossil, to by 2050, we need to get to 50% of the energy mix is non-fossil. Now, so we're now feeling the effects of this energy transition, and primarily on the fossil fuels, coal, oil, and natural gas. But notice from this sort of diagram, we're going to be continuing to use all those for several decades. But there is a question of how much more we actually need to discover as we go forward. So this is probably the single most important slide I'm going to show you today. And in green, in the background there, is world population. I showed you that before. You can see the asymptotic rise. In pink or purple is a really important curve. It's the annual growth rate of world population, which peaked in 1968 at 2.1% and has been dramatically falling since. We're at about 0.8% now, and it looks like it should go, under current predictions, to 0.1% by 2100. But what I've put in there in the red bars is the time between now and 2050 when we actually have to accomplish this change in our energy usage if we're going to try and actually stabilize climate. And what's really important to note is that's one generation. So most of you in the audience will live to see this. And if you won't, your kids certainly will. So one generation to make an incredible change in our society. That's why the young people have been marching, and that's why this is a real serious issue. So where are we today? I think we can see that fossil fuels are losing steam. This is the US, the Standard & Poor's 500 valuation, you can see is rising, even with the drop there of the pandemic. But the ExxonMobil share price, as you can see, is dropping even faster. And the headline from last October, wind and solar producer tops Exxon as most valuable US energy company. This is continuing. This is a headline from last week, from February 4th. Oil company losses in 2020 were staggering. ConocoPhillips announced last week that it lost $2.7 billion in 2020. BP and Chevron each lost just over $5.5 billion, and ExxonMobil posted a loss of $20 billion. So the energy transition is certainly happening. And it's happening in Australia too. I'm showing here the ASX 300 versus the fossil fuel dominated ASX 300 energy. And what you can see is they started diverging in about 2012. That's probably when your energy transition there started. And the ASX 300 is going up. And there is the drop at the end there for COVID, but I'm sure if I had more recent data, it would be coming back up. And we can see that for energy, it's flat to declining. We can look at the human face of this. This is unemployment in Houston, the petroleum capital of the planet. And what we can see there is unemployment goes up and down. It's cyclic, based essentially on oil price. But then when we get to 2020, there's obviously a spike. Now that's COVID, there's no doubt about that. But as we come back out of that, notice we're still at a very high level. And I think this probably is the energy transition happening in Houston. But there's some good news too. This is data from the American Geoscience Institute from just this week, and it shows employment status of recent graduates, 2014 to 2018, geoscience graduates, for last year, February to December. And what you can see is those employed is pretty flat. There's actually no great drop because of COVID. And the green line is non-academic geoscientists, i.e. those employed in industry, and it actually is going up. So some good news. Now, in terms of where people are going, this is on the right. This is the industry sectors that employed recent geoscience graduates as of last December. And what we can see is oil and gas is 4.2% of those that graduated. Other industry is about 2.8, with mining being 0.8%, because mining isn't that important in the US as part of our GDP. Notice that environmental services is 12.1, so 3 times the size of oil and gas. That NGOs are 5.7, so higher than oil and gas. And government is almost 25%, telling you that the government is hiring again in the US. So COVID and the energy transition. This is one of the few things that I think COVID actually is probably going to be good for. So COVID the pandemic has spurred new ways of communicating and conferencing, just what we're doing right now, but I suspect are going to permanently alter the way we travel and the way we work. And these sorts of things really will save significant energy in the long term. So now I want to talk about how the energy transition has affected me personally and our research center, because it really has been a transition the last couple of years. So iCRAG itself, our research center, was established in 2015, and I joined it as a director in the spring of 2018. It's one of 17 state-funded national research centers. And it includes researchers, ours does, from 5 different universities and 2 research institutions. The goals of the center when it started were to help unlock Ireland's natural resources, that being offshore petroleum or offshore hydrocarbons and onshore minerals, to contribute to securing the supply of energy and safe water for the island, to educate and improve understanding of geosciences, and to achieve international excellence in applied geoscience research. And in 2018, when I joined, basically the center had been funded jointly by Science Foundation Ireland, the federal government, 18 million euro worth, and industry, 8 million. And we were working with a number of different bodies, including a number of different geoscience state bodies, such as our Geological Survey and EPA. The partners in 2018, over a third of them were oil and gas companies, including most of the world's major hydrocarbon producers, you can see here. And the center in 2018 had approximately 150 researchers. We had 5 research spokes: raw materials, marine geology, groundwater, hydrocarbons, and geohazards, and 4 research platforms that supported this. And when the center started in 2015 to 2018, when I joined, it basically was dominantly funded by oil and gas money and hydrocarbons were a dominant part of our research agenda. When I joined, it was clear the world was changing. I suspect that's one of the reasons they wanted to hire me, was to bring in a new view. The center itself was funded to the end of 2020. So when I came in 2018, we started writing the proposal for our phase 2. And the world was changing right in front of our eyes. So in 2019, we had thousands of students marching all across Ireland in the major cities every Friday for climate action. And that continued for much of the year. On May 10th, Ireland declared a climate emergency, becoming one of the early European countries to so do that. In June, the Irish government published a climate action plan. And then in September, our Taoiseach, our Prime Minister, announced a ban on offshore oil exploration, but said that gas exploration would remain. Now, between June and September, we had to actually have our proposal ready to go into our funder. And as you can see, things are changing pretty quickly. November 8th, getting towards the end of the year, the government announced that it was closing peat power plants. Peat power here in Ireland was a major employer and a major source of electricity. So this was a very, very large political deal. Okay, we're going to go into 2020. I'm going to get my review back in the spring of 2020 and then have to redo it again for the final proposal. And I'm going to be reviewed in April by an international panel that's going to tell us whether we're doing the right things or not. So the start of 2020, there's a general election here in Ireland. And then in March, we have lockdown, the start of COVID. Here in Ireland, it took a while to form a government. That didn't happen until May. And when the government formed, it was the two major parties plus the Green Party for the first time in three different groups together. And one of the first policies they announced was to ban all hydrocarbon exploration. So not just petroleum, as had been done the year before, but natural gas as well. So that happened basically just as we were putting our second round of proposal in. So we had to scramble yet again. So the description of energy in iCRAG. In 2018, when I joined, it was petroleum focused with natural gas, geothermal, and wind. In 2019, the first proposal we put in was natural gas, wind, and geothermal. And in early 2020, the modified proposal for iCRAG 2 was simply wind and geothermal. And I can tell you that has all sorts of interesting things in terms of how we were going to fund the center going forward in terms of industry and EU proposals. So the impact on iCRAG of the energy transition. Our new center, which was just last week announced that it's funded to 28 million euros, is now organized around three grand challenges: Earth resources, Earth system change, and Earth science and society. And in this whole area, only renewable energy is now highlighted. The hydrocarbon expertise that we still retain in the center is being utilized in reservoirs and storage, so things like geothermal and carbon capture and storage. We're also using it for climate and environment in defining paleoclimate, mainly from offshore geology. And we have significant inputs of that research expertise into our marine and offshore geology research. The center will now have a major focus on raw materials, especially critical minerals, battery metals, and construction materials. Water, which we did before, will remain a major focus, becoming larger. We have a new focus on climate and the environment, and a new focus on responsible decision-making and geoscience, meaning that our center is growing as we add social scientists. So, iCRAG's journey. What does it have to tell us about the energy transition? Doom or gloom? Are you here? So, there's no doubt that an era of significant cyclically available research funding and long-term high-paying permanent employment from the oil and gas industry is coming to an end, at least here in Ireland, and I suspect in Australia as well. So as we go forward, what iCRAG's focusing on, I suspect, is what most major geoscience research groups going forward are going to focus on: water, minerals, raw materials, environmental geoscience, hazards, and climate. And to be honest, these are exactly the areas we need to focus on to address the climate emergency. So if we look at water, well, here in Ireland, we often have too much. There in Australia, you often have too little, and everywhere it's often too polluted. And what this means is there's going to be jobs in water in academia, in industry, and in government. And boy, are there going to be a lot of research problems that are going to go on for decades and decades. Raw materials, my specialty, and what my center is going to be focusing a lot of its time on. So this is minerals and materials. Again, to build the wind turbines that I show here, or any of the technologies we're going to need to change how we actually get energy, we need metals, we need materials. So again, there's going to be jobs in academia, industry, and government dealing with minerals of all kinds, and again, a host of research problems that can be funded. So just look at raw materials a little bit more in detail. We need them for IT infrastructure. So we all talk about the cloud, and especially now that we're zooming around the world, everything's going through and into the cloud. And if you think of a cloud, it's light and fluffy things, and there in Australia, it's during the day, you can probably look out a window and see them. But in fact, the cloud is actually made of metal, right? It's a whole bunch of wires and servers and computers sitting in an air-conditioned room somewhere. Also, technology means it's changing, and so the needs are changing. So on the left is an old, in quotes, satellite phone. For me, I remember before satellite phones, but that's okay. But sat phones used about 30 elements. Today, everyone has cell phones, and they take at least 75 elements. And as they make them more and more impressive, they'll take more elements. And it's interesting to know that things are changing and how they change. I love this picture. It's one I've used in talks for a long time. But this is the top of the Washington Monument. And in 1884, when they finished the Washington Monument, they wanted something on top that was really precious, but also wouldn't tarnish, right? So you know, the choices: gold, platinum, silver. Well, it turned out there was one other metal that was worth almost as much, and that was aluminum, because they didn't really know how to get aluminum back in the 1800s. So the top of the Washington Monument, in fact, is aluminum. It was the same price as silver at the time. Obviously, aluminum now, until recently, just threw the cans away, right? So it's not worth anywhere near what it was 100 some years ago. And that brings us to raw materials and energy and all these things. So here's the same curves for population, for energy, and CO2. They all go up. And not surprisingly, metals production, in this case copper, tracks those too. So as we've gone through all these different things, as we use more energy, as we have more people, we need and use more metal. And then raw materials and building materials. I shamelessly stole these images from the Atlantic magazine because they just brilliantly show what's happening in the world. This is Shanghai in 1987, and exactly the same viewpoint 26 years later in 2013. And what you can see is all of a sudden a modern city appeared, and a big modern city with a lot of buildings. So that takes a lot of concrete, that takes a lot of stone, that takes a lot of metal. This is still happening in China, and it's still happening all over the world. So raw materials, fun facts. I'll talk at the very end about a UNESCO lecture series that's happening, but there's some fun facts from this. One that came out last week was that global copper production is 22 times higher than 100 years ago. And based on those last two slides, this may not surprise you, but China used more cement in the last 3 years than the US did in the last 100 years. And more fun facts, these from Professor Daniel Franks, the program leader at the Sustainable Minerals Institute at the University of Queensland, from 2 days ago, a talk from UNESCO. Metals actually make up a minority of global commodities by production, volume, and importantly, value. So in terms of volume, you can see on the left, metals are 2.8% of total production, total volume, and industrial minerals and construction materials are 84.2%. Second, the majority of mineral commodities produced are not exported. Most of them are mined and used in a very small area. Large-scale multinational mining companies are, relatively speaking, minor players in the global mineral sector. This is really surprising, especially to those of us who work in economic geology and the metals industry, right? We think we're the top of the heap, we're the bottom, right? And this is really important to note. And finally, the vast majority of materials mined are rarely noticed by society. They're in quarries, sand pits, and things like that. And it's one reason they probably get away with it, because they're not mines, right? Mining does have very bad societal connotations, but what this is telling us is most of the mining actually isn't sort of mining we think about when we think of mining. Okay, to move to some of the other areas, environment. Environment is just a huge, broad term, and it includes a lot of things. Geoscience really is foundational, along with bioscience, for what we now term environmental studies. And boy, are there going to be environmental jobs, again, in academia, industry, and government, and a host of research problems that can be funded throughout the energy transition. Climate. Too many people think of climate scientists as modelers, just what the IPCC does. What they do is critically important. What they do also requires a huge amount of data from the present and from past. And these data, a lot of them, come from geoscientists. The public thinks of climate change in terms of the future of the planet. Earth scientists study its past and its present, and what we do is critical to predicting the future. Hazards. They're critical and they're of growing importance with climate change as we respond with both mitigation and adaptation. There's going to be research and jobs that are going to vary from the geotechnical to actually deal with them directly to the statistical. I can tell you that insurance companies are very, very interested in geohazards. When I worked in the White House, surprisingly, I worked with a lot of insurance companies when I dealt with climate change. So there's going to be growing requirements for individuals with skills in geohazards in both the private sector and certainly in government. And the four images here are all from Australia, from I think the last year, showing the geohazards you've been having down there, which I hate to say are legion. So one of my points that I like to make at talks is that biodiversity depends on geodiversity. They go hand in hand. The biosphere, which supports life on Earth, extends upward from the Earth's surface to the troposphere, about 19 kilometers, and down probably about 5 kilometers below the Earth's surface into the subsurface. So that's a total thickness roughly of about 26 kilometers circling the globe. So the biosphere represents approximately 0.4% of the Earth's diameter, which means it's really small compared to the planet. Understanding the geodiversity of this thin band around our planet is actually crucial to preserving our biodiversity. And this brings us back to the Anthropocene. So the biosphere, the hydrosphere, the atmosphere, and the geosphere today are all linked through the human system. And that's something we have to always take into account now as we do geoscience. So I come back to the energy transition. Clearly, there'll be fewer employed in the fossil fuel sector moving forward, but we actually need to preserve what they've actually brought us to this point and how they've got us here. One of the things I like to it's always struck me, I guess from my anthropology, archaeology background, is the Pantheon in Rome. It's a 2,000-year-old building, still standing, and the dome on it, which you see here, is the largest unreinforced concrete dome in the world. Okay, that's amazing. 2,000 years and it's still the biggest humans have ever made. And even more amazing, we don't know how they did it. We don't know how to make the concrete the Romans did. Even though we have mineralogists and material scientists right now trying to figure that out, and they have been for a number of years, we still can't recreate Roman concrete. And that brings me to what's happening right now with the oil transition. We don't want to forget what we know now. For those of you who worked in the industry, you know, the technology and knowledge in the oil and gas industry is absolutely astounding. So how do we ensure that the knowledge and expertise that we have now is not lost and that it's put to use to solve other societal problems, including the climate and biodiversity emergencies? An example, again, that I guess I come from the United States is a number of years ago, at the end of the Cold War, scientists from the Soviet Union and the United States worked together on nuclear arms reduction and tried to limit the spread of nuclear know-how. So perhaps in the climate emergency, some governments around the world, the enlightened ones, should work to preserve and utilize the incredible technology and knowledge of the multinational oil and gas companies. A lot of people are trying to demonize the industry now. I understand that. But there's a lot that the industry has contributed and really can contribute from its knowledge. We need to retain and retrain. And the classic example or prime example is big data and artificial intelligence. The oil industry has been doing big data for several decades. So they have produced and utilized huge amounts of data. They have superb data sets, and they know how to manipulate that data, and they're using machine learning on it. Taken together with machine learning and other geoscience areas, such as climate and hydrology, there is an incredible future for geoscience, data science fusions. So, looking at it, I don't think all is doom and gloom. I think we're actually there with a smiley face, really. If we look at the energy transition, all the other forms of energy shown here, geothermal, wind, nuclear, hydro, solar, they actually all require geoscience materials and geoscience knowledge. And the circular economy, something that I'm not sure exactly how into the circular economy you are in Australia. Here in Europe, it's the bee's knees along with the Green Deal. But geoscience skills are needed throughout the circular economy in the discovery and production of materials, the environmental treatment of all waste produced right along the entire cycle, and material stewardship to ensure that the produced metals and materials stay in use as long as possible so we don't have to produce new ones. So the Ellen MacArthur Foundation states that the circular economy is based on the principles of designing out waste and pollution, keeping products and materials in use, and regenerating natural systems. And this chart now of what we're doing with several of the metals shows that we do have a long way to go. Some metals like lead or aluminum, we recycle quite a bit. But lithium and neodymium, which we need for batteries and for wind turbines, as you can see, 0% and 1%. And even copper, which is used right across all the industries, the IT and the energy, only 17% is now recycled. And I do a lot of work in Africa. So these images are my images from Africa, and I see recycling sort of on a daily basis there. And I must say, those with less economic ability often recycle more than those of us with more economic ability. And maybe we actually need to learn from these people how to do it. And then there's supply chains in the circular economy. And again, I think geoscience is really important here. Geoscience forensic examination of materials when they're produced, in manufactured products, in waste from all stages, from production, manufacturing, and post-usage, as well as geospatial analysis of supply chains themselves, is needed if the circular economy is to be secure. So geoscience is going to be critical to the energy transition, and geoscience knowledge is required to ensure that we successfully address all 17 of the UN Sustainable Development Goals. Sometimes a change of view, say from the South where you are, can help clarify things. I love turning the world upside down. From the first time I went to Australia and saw the world maps that way down there, I thought it was brilliant. So, change of view. Australia today relies heavily on geoscience in terms of its national GDP. Though there will be undoubted change due to the energy transition, with, for instance, reduction of the thermal coal industry and a decline in oil and gas exploration, there will be incredible opportunities. And these opportunities include a booming mineral sector, especially battery metals and IT metals, but also infrastructure metals and building development materials, iron ore, of which Australia is obviously a leader, sand, gravel, and stone. Growing environmental sectors in many different ways. Everything to do with water and the application of geoscience technologies and understanding to supply chain validation and implementation of a circular economy. And finally, the application of oil and gas technologies together with spatial machine learning and AI to multiple societal problems. So before I go, I do want to shamelessly give a plug for this lecture series, Earth Materials for Sustainable and Thriving Society, that iCRAG's organized along with UNESCO and IUGS. We have speakers from around the globe. We've had 3 of the lectures already, and they can be found on the web at the website there. The lectures are ongoing until March 9th, so I encourage you to get on the web and take a look and see some of these lectures if you can. And with that, I'd like to thank everybody. Thank you for inviting me to come to your conference. Tasmania has a soft spot in my heart. I wish I could visit. And I will again at some point once the world gets to its new normal. Thank you very much.